Hi again. So this is the last part of this chapter, kinematics in 2 dimensions. Now in this topic we will mostly talk about projectile motions. Now before we continue, you should know the rules when you want to understand the kinematics in projectile motion. First, you should consider all projectile are free falling object. Second, the horizontal motion, which is x-axis, is totally unaffected by the free fall motions. Last but not least, since there is no forces acting on it, horizontal motions is at constant speed. So the acceleration is equal to 0. Now this is a graph of parabolic trajectory of a particle. It leaves the origin with the velocity of v0 over here. Some of you might denote it as a u0. It's similar. Now, note that v change with time. However, the x components of velocity, which is vx, remain constant in time. So it will be equal with the initial velocity v0x. Also, vy is equal to 0 at the peak of this trajectory over here. But the accelerations is always equal to the free fall acceleration and acts vertically downward. So a is equal to negative g, similar with the one that you learn in free fall. So this figure shows the effect of various initial angles. Notice that complementary angle give the same horizontal range. Right, so in general, our equations of constant acceleration follow separately for both x directions and the y directions. Notice that the initial velocity over here has two components. So let's assume at t equal to 0, the projectile leave the origin with velocity as v0, initial velocity at v0, and if this velocity vector make an angle of theta over here, which what we call as theta naught, with the horizontal, this is what we call, this theta over here is what we call as a projection angle. Then from the definitions of cosine and sine function and this figure over here, we can write these equations for initial velocity in x-axis and initial velocity of y-axis. Right. Since the projectile was launched at an angle, so the velocity must be broken into components, which is, as you can see over here and over here. So this blue line here is our initial velocity v0, where it was launched with the projectile angle from the horizontal positions is equal to theta. So this initial velocity can be separated into two parts. The first one is for x components, we denote it as a v0x, and we have our y component, we denote it as a v0y. And to find this one, we are using the rules of cosine and sines, and we will get this value. Our equation for motion with constant acceleration in one dimension carry over to the two-dimensional case. So on the second video, we have learned about the we have derived our three kinematic equations. Then we bring it over here in our 2 dimensions, and as you can see over here, there is one set of these 3 equations for each direction, x-axis and also y-axis. So we have our velocity in x-axis, in y-axis. We have our change of distance in x-axis and also y-axis. We have our third kinematic equations in x-axis and y-axis. While for this one, we have it from the separate initial velocity that we just derived. Now, the object speed v can be calculated, v over here, can be calculated from the components of the velocity using the Pythagorean theorem. So this is how to find the velocity. And the angle that this velocity make with the x-axis. So if this is our v, this is our x-axis, this is our theta, we can calculate it by using this inverse tangent. So this formula for theta, as you recall, must be used with care, because the inverse tangent function returns value only between negative 90 and positive 90 degrees. So adding 180 degrees is necessary for vector lying in the second quadrant and the third quadrant. Right, so let's write the kinematic equations for the case of projectile close to Earth's surface. So when friction is negligible, notice that the accelerations in the x directions is equal to 0 because air resistance is neglected. This means ax is equal to 0 and the projectile velocity component along the x-axis remain constant. Anything that we have here in x-axis is remain constant. Now if the initial value of the velocity component in the x directions is v naught x is equal to v naught cos theta naught, then this is also the value of vx here. So the horizontal displacement can be written as this one. Now for the motions of in the y directions, we make the substitutions of ay over here with negative g, and v naught y is equal to v naught sine theta. Now let's summarize the important facts about projectile motion. Number 1, provided air resistance is negligible, so the horizontal component of the velocity, which is vx, is remain constant because there is no horizontal component of the accelerations in x-axis, and the vertical component of the accelerations is equal to free falling acceleration. So delta acceleration in y-axis is equal to negative g. The third one, the vertical component of the velocity and the distance in y directions are identical to those of free falling body. Last but not least, projectile motion can be described as a superposition of 2 independent motions in x and y directions. Now, here is an example for you to try on your own first. You may watch how I solve these on separate video of example. And here is another one for you to try. And with that, these chapters end here. You are welcome to continue watch the video, for example, and extra video as your reference to understand more on this chapter. So that's all. Thank you.